Couple of weeks ago, we have looked at the quarter point element, the special finite elements designed to calculate the stress intensity factor at the tip of a sharp crack in a linear elastic material. So now that we have learned about energy methods in fracture, we're going to look at three more techniques which depend on the concept of G or the concept of J. These are more general techniques, and these are some of these, at least one of these, are applicable to non-elastic cases as well. Though we will right now we will apply them to elastic cases only, but we will learn three methods which are based on the concept of G and J. The first method that we are going to learn is called the weight function method. In this weight function method, to understand this weight function method, imagine that you have two load cases on the same body. So this is the body, this is your del VU, the part where displacements are specified. This is del VT, the part where tractions are specified in load case 1. In load case 1, where we want to find the stress intensity factor at the tip of this crack, we have tractions applied at far field or on the face of the crack, and we have a displacement field in the body given by U subscript 1. Okay, N is the outward normal to the surface or the crack faces. Now I have a load case 2 where I don't have any remote tractions applied on the outer boundaries. The del VU is the same as in load case 1, but I have a concentrated force F applied at a distance d from the crack tip, and this F has two components, P and Q, which are equal and opposite on the top face and the bottom face, so that the body is in equilibrium under these two loads. The displacements in this problem, let's say they are given by U2, which is a function of position, and the tractions are T2 in this case. Now, we want to find the stress intensity factors K1 and K2 in load case 1. This is our intended problem, and this is an auxiliary problem that we have chosen, which we will use to find this K1 and K2. So this is the idea, and in the second case, load case 2, let's first go to load case 1. In load case 1, the displacement U1 very close to the tip of a crack will be given by the Williams solution, and if you apply Williams solution to theta equal to plus minus pi, if you apply Williams solution to the displacements theta equal to plus minus pi, you will get these two expressions. So in case of pure mode 2, if you go back to the displacement equations, you will see that U1 in load case 1 is this quantity, where the plus is for the upper crack face, minus is for the lower crack face. This is for pure mode 1. Sorry, this is for pure mode 2, and for pure mode 2, U21 is equal to 0 at theta equal to plus minus pi. Similarly, this is for pure mode 1. This is for pure mode 1. U2 is this, again plus is for the upper crack face, minus is for the lower crack face, and U11 is equal to 0 at theta equal to plus minus pi. You can easily verify this if you go back to your general expressions for the displacements that we had given many weeks ago when we did LEFM and Williams solution. So the displacements in the first problem, at least close to the crack tip, close to the tip of the crack, are known in terms of the K11 and K21 that we intend to find. In terms of these, the displacements close to this are known. We will use this fact, we will use Williams solution now to couple with this problem, with this auxiliary problem, and find K1 and K2. This is how we are going to do it. So let's turn to load case 2 now. This is load case 1. So the superscript 1 tells you that it's load case 1. Let's turn to load case 2 now. In load case 2, you have a point load F, which has components Q in the x1 direction and P in the x2 direction applied on the crack face. So if you, this is Q, this is P, and on the lower face it is minus Q and it is minus P. So this force F can be represented as plus QE1 plus PE2 on the upper face, minus QE1 minus PE2 on the lower face. And this acts at x1 equal to minus D. This concentrated force using these delta functions at x1 plus D can be expressed as a distributed traction. So this distributed traction can be written as plus minus delta x1 plus D. So this is non-zero only at x1 equal to minus D, is 0 everywhere else, times Q. Similarly, T2 in load case 2, can be written as plus minus delta x1 plus D P. Okay, so we have used these distributions earlier also, so you must be familiar with the use of these delta functions to convert concentrated loads into distributed tractions. This is a standard practice that we have followed everywhere, and definitely in your elasticity courses you must have seen examples of this. Now we are going to use one more theorem from your elasticity course, which is the reciprocal theorem. And the reciprocal theorem is, if you remember, if you don't remember, please go back and learn the reciprocal theorem. We are dealing with a case where there are no body forces, there are only surface tractions, either on the outer boundary or on the crack faces. And then the reciprocal theorem tells us that tractions in problem 2 acting on displacements in problem 1 integrated over delta V is equal to tractions in problem 1 acting on displacements over problem 2, again over delta V. This delta V includes the crack faces as well as the rest of the boundary. So we open this up. So I is a repeated index, so T1 2 U11 plus T22 U21 integrated over delta V is equal to T1 1 U12 T21 U22 over the same delta V. And now out of these, the left hand side can now be evaluated. So to evaluate the left hand side, we know that T12 is this quantity, T22 is this quantity, and at least close to the crack tip, we have U11 and U21 given in terms of K1 and K2. So if I use that expression, then I can easily convert this integral, put the value of T12 and T22, and we will find out, then put the value of U11 and U21, we will find out that this is the result of the integral. This is the result of the integral. This is very easy to find given the fact that when you multiply delta x1 plus d with fi being either q or p. F1 is q, F2 is p, or F1 is minus q and F2 is minus p. In that case, this picks out the value of F1 ui1 at D. So at D, Fi is either P when I is equal to 2 or Q when I is equal to 1, and at minus D, because this is x1 plus D. So and you are left with u1 at minus D. Okay, so so you are left with u1 at minus D, and u1 at minus D is known from this expression. U1 1 is this, U2 1 is this. So U1 at minus D is known to us, and we can write U1 1 contains K2, U1 2 contains K1, and given that, we will get this entire expression as the result of this integral, which is nothing but the left hand side of this equation. So this integral, this expression can be used as it is, but we will now look at a case where we have pure mode 1. That means we are, just for simplicity's sake, taking load case 1 to be a pure mode 1 case. Okay, this is what I am using to demonstrate the method. The method is not limited to a pure mode 1 case. It can be generalized, but just to make the idea clearer to you, I am using a load case 1, which is a pure mode 1 case. So when it's a pure mode 1 case, then this term is equal to 0, because K2 by definition is equal to 0 and Q is also equal to 0. Therefore, this expression, this left hand side here, this expression now becomes d by pi, root d by pi pk11 is equal to this thing times the right hand side of this. So this right hand side, which is delta v ti1 ui2 ds, this right hand side, times this quantity taken to the other side, gives you this expression. Okay, so now to get K11, which is what we want to find, because we already have chosen a case where K21 is equal to 0, we have only K11 to determine. To get K11, we need to determine this integral. So this idea was used in this paper by Buchner in 1970, and then also expanded in this paper, which has become a ASTM standard, ASTM STP, I think 65. So this is now a standard method for calculating stress intensity factors through finite element computations. And this can be solved using a solution given by Buchner. Buchner gave the solution for K1 when the load is infinitesimally close to the crack tip, which means instead of being located at D, the load is located almost exactly at the tip of the crack. For D tends to 0, Buchner gave a solution to the full solution to the problem of load case 2. So we know the solution of load case 2 through Buchner's method for the case where d tends to 0. So, so if I take limit d tends to 0 on both sides, you see that the right hand side does not depend on d. So this limit, taking this limit and not taking this limit is the same thing. But on the left hand side, Buchner has given a solution to p delta root d by pi with d tending to 0, and that solution is, let's say, that limit is, let's say, given by b1. So this is available from Buchner's solution. This is available from this is for mode 1. He has a different solution for mixed mode and mode 2. We are not going into that. There are other Buchner solutions for other modes, but we are only interested in the mode 1 solution for the time being. So this limit is known. This limit is known, and therefore this limit is known and is equal to b1 according to Buchner's solution. So then k11 would be just this whole thing divided by b1, and that's what we have here. So basically we have to solve this integral, know b1, and then we have the solution to the k11, which is what we want to find. Okay, now we define a weight function now, and the weight function is defined in this manner. So k11 is equal to ui2, which is a function of x, times ti1 ds. Now this whole thing is called the weight function, and this, if this is I, this weight function is called hi1, and it's a function of x because ui2 is a function of x. So this weight function is, this is my definition of the weight function for this problem, and this, once this weight function is known, then k11 is the integral over delta v of the weight function times the traction integrated over delta v. Okay, if we know this weight function. How do we know this weight function? To know this weight function, we need to know the Buchner solutions. So so these are the Buchner solutions for the problem where you have a crack. This is x1, x2 at the crack tip, and you have loads applied infinitesimally close to the crack tip. You have these loads P applied infinitesimally close to the crack tip. You don't have Q in this case because these are the mode 1 solutions, and these are the displacements and these are the stresses. We don't need the stresses at the moment, but the displacements, as you can see, are unphysical because they have this 1 by square root r, which makes the displacements infinite at the crack tip, which makes the energy at the crack tip also, energy density at the crack tip also infinite. However, this is unphysical, but okay, we want to just use it as a weight function, and we are not really worried about the unphysical nature of the solution. Now, we are interested in the solution at theta equal to plus minus pi, which is on this crack face or the lower crack face. For, let's say, pi, plus pi, this is 0, and this is 2 into 1 minus nu, and this is 0 again. So for theta equal to pi, we have u12 is equal to 0 and u22 is equal to b1 by mu root r into 2 into 1 minus nu. Okay, b1 by mu root r 2 into 1 minus nu. And then if I go back to the previous slide, this was my weight function. So h11 at any point is 2 mu by kappa plus 1, 1 by root 2 pi, u12 by b1. Okay, but as we see, u12 is equal to 0, which means that this is equal to 0. However, h21 is equal to 2 mu by kappa plus 1. So kappa plus 1 for the plane strain case is 3 minus 4 nu plus 1, which gives you 4 into 1 minus nu. So this is 2 mu by 4 into 1 minus nu, 1 by root 2 pi, 1 by b1 times u2 is b1 by mu root r is b1 by mu root r 2 into 1 minus nu. Things cancel out, this cancels out, the mu cancels out, b1 cancels out, and this becomes 2, the root r remains, and finally the root r on theta equal to plus minus pi is simply x1. Okay, so what you get as shape as weight function is h11 equal to 0 and h21 is equal to 1 by root 2 pi x1, r becomes x1, and if you do it at minus pi, you will get minus of this. So I have written plus pi and minus pi together, so it is plus minus 1 by root 2 pi x1. So this is the weight function that we will have to use in mode 1. So let's work out a problem using this principle. We have this Griffith crack length 2a from my x1 equal to minus a to plus a. But unlike a Griffith crack, this is subjected to attraction which is of this form. So on the top, this is equal to sigma naught root over 1 minus x1 square by a square, and on the bottom it is sigma naught root over the minus sign. So this is of course a mode 1 situation, so we can use the mode 1 weight functions, and we will use this expression here. We'll use this expression here to find k1 1. K11 for mode 1 will be h I1 is, we know that h11 is 0, so h21 t21 ds. Tractions are only over the crack surface, so we are going to do this integration from minus a to a. It's a mode 1 problem for both crack surfaces. We'll do this. So to calculate this, we remember that the weight function is this, but this was at a crack for a crack tip coordinate. here we have a coordinate to the middle of the crack. So if you put a coordinate here and this is your x1 in the centered coordinate system, then this is a minus x1. So here we must replace this by a minus x1 for our coordinate system, and then integrate from minus a to a. For the lower crack face, it's the same, so I have this 2. When you do this, I do this approximation because we are trying to find things very close to the crack tip. Since we are trying to find things very close to the crack tip, I make this approximation that this quantity, this times this, is we can do a binomial expansion and write it in this form. If you do this, then you immediately find that this is the stress intensity factor, mode 1 stress intensity factor for this particular problem. So this is your load case 1. You have load case 2, which is your Buchner problem, and using the results of load case 2, you find the results of load case 1 for an unknown, for an arbitrary traction distribution like given here. So how is this implemented in a finite element mesh? So here is a specimen. This is a mode 1 specimen. So half of the specimen is modeled. Here's a crack of length A. The width of the specimen is B and the height is H. This problem is taken from this reference. As I said, this is now part of our ASTM standard. So you can look up the standard and find more details about this simulation. Now, what is done in a finite element simulation is that in front of the crack, you make a very small hole. This hole has a radius of r, and r is extremely small, and this is that hole, and you mesh it around the hole. So on all nodes on the periphery of the hole, you apply the Buchner displacement solutions. That means you apply these displacements. So at a given r, and for theta varying from 0 at the right edge of the hole to 180 at the left edge of the hole, you vary theta, you get u12 and u22, and you apply that on this. That means at the tip of the crack, you are generating the Buchner fields forcibly in this sample, and let me go back to it. Yeah, you are generating the Buchner displacement and stress fields by giving these Buchner displacements along this periphery of the hole. And on the symmetry line, you have to set the u2 displacement to be 0 all along the symmetry line, so that you model the symmetry of this mode 1 specimen. So you have generated, by applying this, you have generated u2 as the Buchner solutions forcibly in this sample. Now, once you have done that, then you can load this sample in any which way you like, as long as mode 1 is satisfied. So now you can calculate the stress intensity factor computationally. You know the tractions that you have applied, T21 and T11 and T21 that you have applied for your problem, and these are the Buchner fields that you have generated. So using this formula, doing this integration all over your sample, or all over the edges on which you have applied tractions in your sample. So you can calculate this integral, and that will give you the K1 for your for the sample that you have chosen. So several mode 1 scenarios can be generated. One scenario could be where you apply equivalent symmetric loads at the two ends. This is a mode 1 case. Another mode 1 case could be where you apply a point load at the middle. Another mode 1 case could be where you apply moments at the two ends. So these are all possible mode 1 cases that you can solve, and for all of these mode 1 cases, the T1 obviously changes. The T11 and T21 changes, but U2, U12 and U22 remain the same. That's a Buchner solution that you have generated, and hence you can calculate this integral numerically. So that will give you the K1. So this is what we do in a finite element simulation. And for more information on how to do this, if you are interested, you can look at this reference.